Hi everybody, and welcome to the concluding video for Chapter 1. In this video we'll cover Section 1.6, which is about Arrow's impossibility theorem. And I have to admit going in that this is one of my favorite sections of the textbook, and it's some of my favorite material for the course. I enjoy all of the material for the course. I think it's all fun, but this section in particular I think is the most fun. And part of the reason is because this section is extremely mathematical to me. So when I think of mathematics, I don't think of computing, I don't think of doing addition or subtraction or things like this, although those things are math, of course. What I think of is I think of abstraction and logic and using logic to make deep observations about things. And that's what this section is about. So if you don't really have a good conception of what math is, and you may, I don't know, keep that in mind as we move through this section. To me, as a mathematician, this section is extremely mathematical, and the material is just extremely cute. I really like this section. So the section deals with sort of this fundamental question: of all the voting methods out there, which one is the best? So we have been looking at 4 different voting methods, 4 different ways of declaring a winner in an election. And so, of course, there are more than those 4 voting methods. If you look in the homework in the section, they'll show you some extra methods. There are literally hundreds of ways to think about declaring a winner. There's Buckland voting, Coombs voting, modified Borda, modified plurality with elimination, and so on. So there are just hundreds of these methods out there. We only covered 4. Which one is the best? And so you can think about what you might answer. When I posed this question in class, the students, I believe the most popular answer was Borda count. So we did a plurality voting, I guess, to choose our favorite voting method, and Borda was the most popular. And I asked students, well, why do you like Borda the best? And I think the most common answer was, well, it lets you express your full opinion, and they really liked the point system. They liked that second place counted for something and third place counted for something. And so I said, okay, so by best, I suppose you mean some sort of point system, right? You mean something that takes different votes into proportional account. And they said yes. And so I said, okay, that's fine. I suppose you all in class know what you mean by best, but it's actually not clear what it means for something to be best or what it means for something to be fair. So here are 2 related questions here. Which one's the best and which one is fair, most fair? If you're going to ask questions like this, you really need to be careful about what you mean by best or by fair. What does it mean for a voting system to be the best? What does it mean for for one voting system to be better than another? What does it mean for a voting method to be fair? If you really sit down and try to write a definition of these words in this context, it's extremely difficult. And actually, mathematicians and social scientists for more than 200 years tried to answer this first question. I guess it's been more than 300 years now. They started in the 1700s when modern democracies, started coming into existence. And so, of course, if you have a democracy, you want to know what's the best way for people to vote. And mathematicians and social scientists struggled with this for years, for centuries, and they were unable to come up with an answer. And one of the main reasons they couldn't find an answer is because they couldn't define really what it means for one voting system to be better than another. What do you mean by that? And so in the 1940s, a mathematician named Arrow, so you notice the title of this section is Arrow's Impossibility Theorem. Arrow is actually the guy's name, so it's a pretty epic name. Arrow was sitting around and he thought, okay, this first question is too hard. I don't really know how to define the word best in this context. So he focused all of his energy on the second question. What voting method is fair? And in particular, if you're going to ask that question, you have to answer this third question. What does it mean for a voting system to be fair? And he spent several years thinking about this, and he actually could not come up with a complete definition of fairness. It's actually extremely difficult to define what you mean by fairness. But he came up with a sort of a partial definition, and he gave 4 criteria for a voting method to be fair. And that's what we're going to spend the bulk of this section on. So he didn't give a complete definition of fairness. He said, well, if a voting system is going to be fair, here are 4 things that need to happen. So here are the 4 things that it came up with that are pieces of fairness. So in an election using a fair voting method, a majority candidate, in other words, a candidate who gets more than 50% of the first place votes, should be the winner. And this is called the majority criterion. So let's make sure we understand exactly what this is saying. So imagine an election in which you are a candidate. You're a candidate who gets more than half of the first place votes. You get, let's say, 55% of the first place votes. Suppose, though, that you end up losing to another candidate. What would your reaction be to that situation? I imagine your reaction would be, this is not fair. How could somebody else possibly win when I got more than half of the first place votes? I don't find this to be fair. And if that is your reaction, then Arrow is agreeing with you. He's saying, yes, part of what it means to be fair is that somebody who gets more than half of the first place votes should win, with no exception. Okay, and that's what his majority criterion is saying. If a voting system is going to be fair, then somebody who gets more than half of the first place votes should win. Okay, his second condition, or his second criterion, is called the Condorcet criterion. And it says the following: if an election has a Condorcet candidate, then that candidate should win. And we've mentioned Condorcet candidates now in 2 different videos, the first one and the one on section 1.5, the one we just finished. And so if you don't remember what that is, you should go back and review it. But essentially, a Condorcet candidate is somebody who wins all of his or her head-to-head matchups with each of the other candidates. So you are a Condorcet candidate if I compare you head-to-head against every other candidate and you win every one of those matchups. So in voting theory, a Condorcet candidate is seen as a good candidate. It's seen as a candidate who represents the voice of the people. How could it be otherwise, right? If you win every pairwise, if you win head-to-head against everybody else, then shouldn't you be the winner? And that's what Arrow is saying with his second criterion. So again, let's imagine an election in which you are a candidate. Okay, you're a candidate, and after all the votes are tallied, you notice that you are Condorcet, which means that you notice that you win against every other candidate head-to-head. Suppose you notice this, but suppose you also lose. What would your reaction be? I imagine your reaction would be, this is not a fair outcome. Right? I'm Condorcet, I win head-to-head against everybody else, therefore I'm the true voice of the people, I should be the winner, and it's not fair that I lost. If that is your reaction, then Arrow is agreeing with you, and that's why the second criterion is here. Okay, the third criterion, the monotonicity criterion, says that if candidate X is the winner, X should still win if a voter decides to change his mind and rank X higher. Okay, so maybe maybe a voter whoever used to have X ranked third, but decides to go ahead and move him up to second or first. What this criterion is saying is that should not hurt the candidate. You should not be able to hurt a winning candidate by ranking that candidate higher. Okay, so again, imagine you are a candidate in an election, and you are going to win the election. If everything stays the way it is, if all the voters vote the way they say they're going to vote, you're the winner. Suppose, though, that some voters, let's say a couple of voters, decide that they actually like you more than they originally thought. So they used to have you ranked third on their ballot, and now they're going to move you up to first. Right? Suppose that after those voters do that, you end up losing. So let me just summarize. You were going to win. Some voters decided to rank you higher on their ballots, and them doing that caused you to lose. What would your reaction be to that situation? You would say, this is absurd, and it's not fair. Right? You would say, how is it possible that people ranking me higher could make me lose? That's not fair. If that's your reaction, then that's Arrow, once again, is agreeing with you. That's what his third criterion is saying should not happen. The last criterion, called the irrelevant alternatives criterion, says that a winner should not be hurt if one of the losers drops out. Okay, so if candidate X wins, then X should still win if one or more of the losing candidates had not been in the race or they drop out. However you want to read that. Okay, so again, imagine that you are a candidate in an election, and right now you're winning. But after the votes are cast, let's say that another candidate, candidate Y, sees the writing on the wall, sees he's going to lose, and so officially withdraws from the election. Okay, candidate Y says, I'm out. Suppose that candidate Y doing that causes you to lose. Okay, so you were going to win, a losing candidate dropped out, and now you're a losing candidate. What would your reaction to that be? I imagine you would say, that's not fair, right? A losing candidate should not cause me to lose simply by dropping out of the race. If you feel that way, then Arrow agrees with you, and that's why he's saying that criterion 4 should be that kind of thing should not happen in a fair voting method. Okay, so here are the 4 components of fairness that Arrow came up with. So he did not come up with a complete definition of fairness. So there may be other things out there that make up fairness, but what he's saying is, at the very least, these 4 things should happen in a fair voting method. Here are 4 things that should always happen. Here are 4 criteria that make up fair voting. Okay, so let's play with these criteria a little bit. So let's first do this question. Here's a 3-candidate election. Let's find the winner with plurality with elimination. And then let's see what happens when the last 2 voters change their mind and decide to rank C higher. That's what this is saying. So they like C better than A. They change their ballot to CAB rather than ACB. Let's build a new preference table for that and find the winner. And let's see if moving C up in the rankings helped him or not. Okay, so we're going to go through this quickly because we've already covered how this goes. But plurality with elimination, how does that go? Well, C has 10 first place votes. A has 9, 7 from right here, and 2 from over here. And B has 8 first place votes. So B gets kicked out. Once B gets kicked out, C gets those 8 votes. So now C has 18 votes, and A has 9, and C wins. So according to the original preference table, C is the winner, according to plurality with elimination. So let's see what happens when these 2 people in this final column decide to rank C higher. So notice in this original table it goes ACB, C is ranked second. In this new table, C is ranked first. Okay, so these last 2 people changed their minds and they decided to move C up. Let's now see what happens. Well, now A has 7 first place votes, B has 8, and C has 12. So now the first person to get kicked out is A. A gets kicked out because he has the fewest first place votes. When A gets kicked out, his votes are transferred to B. So B now has 15 votes to C's 12. So B wins this new election in which C was moved up. Okay, so just to summarize here, in the original election, C won. 2 of the voters decided to rank C higher on their ballots than they originally had him, and that action caused C to lose. Right? That's absurd. C should not be hurt by having other people rank him higher, right? That should only help him in a fair voting method. And since we can find an example like this, the technical language we use is plurality with elimination violates the monotonicity criterion. Okay? Monotonicity criterion says this should never happen. And we found an example in which it did happen. So before we move on, let me just point out that I'm not saying this always happens. I'm not saying that if you use plurality with elimination, you always hurt somebody by moving them up. All I'm saying is that it's possible to do it. Okay? You can have that happen. And you really should never have it happen if you're dealing with a fair voting method. Okay, so now let's look at a different voting method. Let's look at plurality. And let's play with the Condorcet criterion. So I just want to point out here real fast, again, we've done this before, so I'm not going to spend a lot of time on it. B is the Condorcet candidate. If you compare B to A head-to-head, what happens? Well, these 13 people, right, these 13 people like A better than B, but these 11 people and these 8 people, so 19 total people, like B better than A. So B wins a head-to-head matchup with A. If you look at a head-to-head matchup of B and C, these 13 people and these 11 people, so that's 24 people total, they like B better than C, and only 8 people like C better than B. So B also wins a head-to-head matchup against C. So B is Condorcet, which means that morally he should win, but A wins according to plurality because he has the most first place votes. So, because an example like this exists, you say plurality violates the Condorcet criterion. And again, let me just emphasize, we're not saying that this always happens. We're not saying that plurality will never choose a Condorcet candidate. I'm simply saying that this can happen. It is possible for Condorcet candidates to lose if you're using the plurality method. So let's now play with the irrelevant alternatives criterion. We're going to use plurality again to see how that goes. Okay, so in this example, notice that C loses and A wins, right? A has 13 votes, first place, compared to B's 11 and C's 8. Okay, so A wins and C loses. So let's just ask the question, if C were to drop out of the election, what would happen? Well, if C leaves, right, C drops out, these 8 people like B better than they like A. So if C disappears, these 8 people would now vote for B over A. Okay, so but if C disappears, these 8 people now are voting for B, so B now has 19 total first place votes, 11 from this column and 8 from this column. And 19 first place votes beats 13 first place votes. So B would now win if C drops out. So just to summarize what happens in this particular example, A was going to win, a losing candidate dropped out, and that caused A to lose. A now would certainly feel like something unfair had happened, and what in particular has happened here is the irrelevant alternatives criterion has been violated. Okay, so it turns out that plurality doesn't violate the majority criterion or the monotonicity criterion. So you can think about why these are true. It's easier to show or to explain why plurality doesn't violate the majority criterion. I mean, if you just think about it for a second, the way that you win using plurality is if you have the most first place votes. If a candidate has a majority of the first place votes, then they have the most first place votes. Okay? So if you're using plurality, it is impossible for a candidate to have the most first place votes, a majority of the first place votes, and lose. Okay, it's impossible for that to happen. And it turns out that you can't hurt somebody by moving them up in the rankings using plurality. Okay, so plurality fails a couple of criteria and passes the other two. It fails irrelevant alternatives and what was the other one we just did? Condorcet. But it passes majority and monotonicity. Okay, so now let's switch our attention to Borda count. We've dealt with plurality and plurality with elimination. It turns out that Borda count can violate the majority criterion. And here's an example of that. Notice in this election, A has a majority of first place votes. He doesn't just have the most first place votes, he has a majority of first place votes. There are 11 voters, and A has captured 6 of them for first place. Okay, and I'm not going to write it out, but B wins using Borda count. You can write out the point system yourself and see that B gets more points than anybody else. So what's happened here, A had a majority of first place votes, yet he lost. So if you're candidate A, you probably feel like something unfair happened to you, right? I got a majority of first place votes, yet I still lost, right? That doesn't seem fair. So Borda count violates the majority criterion. So it turns out that actually the only criterion that Borda doesn't violate, the only criterion that Borda satisfies, is the monotonicity criterion. So it violates the Condorcet condition, which means that you can find examples of elections in which a Condorcet candidate loses using Borda count. And you can find examples of elections in which a winner is hurt by a loser dropping out. Both of those bad things can happen. Yeah, as it says here, if candidate X wins an election using Borda, X could not be hurt if people decided to rank him higher. So Borda count satisfies the monotonicity criterion. And if you think about it, that makes sense, right? Because if you move a candidate higher in the rankings, the candidate now gets more points, right, in Borda count. Borda count's a point system. If you rank somebody higher, they can only now get more points. So no, you cannot hurt somebody by moving them up using Borda count. So to sort of summarize everything here, there are 16 spots in this table, in the interior of the table. I didn't show you examples of all of these, but here's a summary of what happens. So this table shows you which methods violate which criteria. So yeah, so the question that's answered in the table is this: does the voting method violate the given criterion? And you don't want to violate, right? Violating a criterion is bad. So if the answer is yes, that's bad. So notice in this table, plurality does not violate majority. That's good. It does not violate monotonicity, but it does violate Condorcet and irrelevant alternatives, which we already knew. Notice that using Borda, as we already pointed out, right, it can violate majority, it can violate Condorcet, and it can violate irrelevant alternatives. Plurality with elimination does not violate majority. It can violate Condorcet, it violates monotonicity, and it violates IIA, violates irrelevant alternatives. So you can find examples in which Condorcet candidates lose. You can find examples in which you can hurt somebody by ranking them higher. We did an example like that at the beginning. And you can find examples in which a winner is hurt by a loser dropping out. Pairwise comparisons actually does pretty well. It does not violate majority, does not violate Condorcet, does not violate monotonicity. So in other words, using pairwise comparison, a majority candidate always wins. Using pairwise comparison, a Condorcet candidate always wins. Using pairwise comparisons, you cannot hurt somebody by moving them up. However, using pairwise comparison, a winner can be hurt by a loser dropping out. So notice all four of the voting methods violate that one. Okay, to summarize what we've done so far, all of the four voting methods that we have studied have violated at least one fairness criterion, right? So that's bad because we're hoping to find a fair voting method, right? If you live in a democracy, you would like to have a voting method that is always fair. So one thing we could try to do is try to find another voting method and study it, right? That's one thing we could do. I doubt that that's something you want to do. We've already spent 4 sections on 4 different voting methods, so it seems like studying other voting methods would be overkill. And in particular, if we could find a voting method that was better than the 4 we just had, if we could find a voting method that was always fair, then wouldn't I have just taught that one method to you from the start, right? If we could find a voting method that's always fair, then I have wasted your time by teaching you about these other 4 voting methods that are not always fair. So that raises the question, can we find a voting method that is always fair? Right? So again, there are hundreds of voting methods out there that we could look through, and we could try creating our own and seeing if we could make something that's always fair, that always satisfies those 4 criteria. Can you do such a thing? And Arrow's achievement was to prove that no. If you have an election with 3 or more candidates, more than 2 candidates, there is no voting method that satisfies all 4 fairness criteria. Okay, so forget about the 4 methods we've looked at. Think about the craziest voting method you want to invent on your own. And again, you could look through the homework of your book and look at Buckland voting and Coombs voting and I forget the other ones. There are more. There are all sorts of voting methods out there that you could look through. And what Arrow was saying is, it doesn't matter what voting system you come up with. It doesn't matter what method you use. You cannot create a voting method that is perfectly fair if you're going to have more than 2 candidates. Okay, so it's hard for me to overstate the importance of this theorem in the social sciences, right? I mean, for hundreds of years, mathematicians and social scientists have been trying to create a fair voting system, right? And what Arrow is saying is you actually can't do that if your notion of fairness agrees with mine, right? If your notion of fairness consists of my 4 fairness criteria. So it's a remarkable achievement, and I cannot explain to you why it's true because the proof is beyond the scope of this course. But you can imagine, how would you prove something like this, right? It takes a lot of work because what Arrow has to do, if he's going to prove this to you, he has to be able to take any crazy voting method anybody thinks up and explain to you why it violates at least one of the fairness criteria, right? That is not a trivial thing to do. So I can't explain to you how he did that, but this is the theorem, and this is what he managed to prove. So a consequence of this is that you can't have a perfectly fair voting method if your notion of fairness is arrows for fairness criteria. So what that means is there's potential for unfairness built into every election, right? There is just there's no way to always be satisfied that the candidate that won is the candidate that should have won under some sort of notion of fairness. But on the other hand, it's not all doom and gloom, right? This doesn't mean that every election is unfair, right? It doesn't mean that every time we have an election, something unfair has gone on. And what it does is it actually leaves room for improvement. There is always room for improvement if you can't have a perfect system, right? So we should always be trying to improve our method and our voting experience. Okay, but this theorem here is the culmination of the chapter. We've studied multiple voting methods, and we've seen some pros and cons with each. Essentially, what this theorem is saying is you cannot find a voting method that's all pros and no cons, right? Especially in reference to these fairness criteria. No matter what voting method you think of, even beyond the 4 that we've done, right? You cannot create a voting method that satisfies all 4 notions of fairness. And that's the end of chapter 1.